Okay, well, welcome to the Collider Phenomenology lectures. You can see my slides there. So, you know, Collider Phenomenology is a very broad topic, and we have 7 lectures here. So this is very much going to be a sort of brief overview. But there are, there are many nice resources out there, and a very non-exhaustive list is given there. I mean, a very classic book is this old pink book, which is so-called pink book, QCD and Collider Physics, which is certainly rather old, and there are newer ones, but certainly covers some of the kind of key elements in a nice way. But there are many other much newer ones, and of course, lots of nice lecture notes out there as well to delve into the details. Now, I'm started with slides, but really I'm going to give the lectures, well, on a blackboard, as it were, on the iPad. And I'm going to make use of these slides only to show you a few plots now and then, which, things which I can't draw, essentially. But yes, the main bit will be indeed given, as I'll start now, directly on the blackboard. So yes, so let me make a start. So Collider Phenomenology. Bit of a mouthful. So perhaps a nice way to start is by drawing a typical LHC event. Very schematically, we've got a proton-proton collision. So let me draw it like that. There's our protons coming in. Some sort of collision will happen again, but that is another blob. And then some particles will come out, which we'll calculate. But then one can get all sorts of radiation like that. And these things could be jets. Generically, there will be, so all sorts of particles in there. And this thing here is the hard scatter. And these things here go under the name of PDFs, parton distribution functions. And, the idea of Collider phenomenology is to sort of relate all of that to, if you like, the Lagrangian of the standard model, or beyond the standard model, the kind of things you've been learning about in your other lectures. And there's obviously, quite a lot of elements in going from the left to the right-hand side here. And so, yes, in essence, the question is, how can we, how can we use this sort of event, let's say, to discover new physics, or, to understand the standard model better. So maybe the first statement to start with is that the LHC is a QCD machine. It's sort of implied in the drawing I've shown you there, which is that, the hard scatter here could be Higgs boson production or SUSY particle production, maybe, or whatever else, some electroweak process. But always one has the fact that one is colliding protons, and inevitably there's going to be lots of QCD radiation and all this sort of stuff going on in the final state. So you can never really get away with that. So that's the kind of the first key statement. And because of that, and because of the limited time, a lot of the focus here will be on that QCD element, because it's always there. You always need to understand it, and there's some key tools that you need to understand to make that relationship I've just talked about. So the main focus here is going to be on understanding how we deal with that, let's say. And so there's a few kind of take-home things. You'll have seen this already, which is that strong coupling at NZ is of order 0.1, so we can use perturbative QCD. But that's not enough. You also need a separation of your short distance, your high energy from your long distance. And that's something we're going to talk about. And if you don't have that, then it doesn't matter that you can calculate your hard scattering in perturbative QCD. one can never make predictions because you always have this long distance physics going on in there, be it the formation of jets or the binding of the quarks and gluons into the protons. And so things like so-called factorization and PDFs, the kind of things we'll talk about with respect to that. And you know, in that vein, sort of soft collinear radiation, parton showers, resummation, and jet physics. Okay, a lot of things being listed there. Of course, I'm going to tell you about them in due course. And then finally, some of the tools of collider pheno. And there are, you know, you could really fill an entire book with all the different tools for all of the different sort of things you want to do in a collider, and I obviously can't cover all of them, so I'll just highlight a few key things in that respect. So again, you know, it's a brief overview here. Brief, but I want to at least, you know, go into the calculations of some things and not be completely superficial. But by its nature, that then means that there's many things I won't have time to talk about. And for those who are interested, you can of course find more details elsewhere. Yeah, one other thing is that, you know, a lot of the time I'll deal with leptons. In the initial state. So we'll see that in a minute, which is clearly not what happens at the LHC. I've just talked about protons. It's a proton collider dominantly, certainly not a lepton collider. So, you know, this is not what happens at the LHC, but is easier way to introduce some key elements. So, you know, at some points I'll be talking about things that happen in E+, E- collisions or electron-proton collisions. And if you're an LHC physicist, or even if you're not, you might kind of think, well, who cares? You know, why is this relevant? Well, while those things are interesting in their own right, but the elements, the bits of QCD that go into understanding those sorts of interactions also directly translate to the LHC. Okay. So let me start. So as promised, I'm going to start with something featuring leptons, which is E+, E-, so hadrons. So let's recall from our QED lecture, QED lectures, which you will have had or will be having, that you know, that d sigma d cos theta for f bar, so fermion antifermion, goes to some other fermion prime, antifermion prime. So you'll have seen that in the context of E+, E- to mu+, mu- in QED, but it's a sort of, one could easily replace them with other types of fermions, and what you end up with is the sort of let's call it an FQ and an FQ prime squared. So those are the fractional charges of the particles. Alpha squared pi over 2s times 1 plus cos squared theta, where probably not in this lecture and even in the next lecture, but I will make use of it at one point in terms of your Mandelstam variables. That's u squared plus t squared over s squared, but that's actually not relevant for now, but let me at least indicate it because I'll make use of it later. But okay, there's the expression. And you know, let me draw it in green, for example. The kind of Feynman diagram look like something like this. So there's our fermion, and there's our fermion prime. Okay. And again, yeah, we do that in the context of QED, but let's generalize that. So what about E plus E minus dihadrons? Well, indeed, as you actually saw in your QCD part of the lecture, maybe rather briefly, the idea here is that we consider quark antiquark final state. Okay, I'll come back a little bit more about the connection between that and the fact these things are hadrons in a little bit, but clearly, if we're going to produce hadrons, you need to produce quarks and antiquarks, and that's the kind of the lowest order diagram you can draw. So that's the kind of basic idea. And so we have, again, this is sort of recapping what you had perhaps, which is that the ratio of E plus E minus to hadrons over E plus E minus to mu plus mu minus, which we define to be this thing called R, is equal to NC, the number of colors, times the sum over the fractional charges of the, sorry, I think I called that FQ squared, where this is then a sum over all of the different quarks that one can produce, provided that the center of mass energy is large enough. Okay, very good. So let me just jump to a few slides at that point. So again, that's the picture we're going at first of all, which is that that's really what it would look like in a cartoonish way at the top there. But what we're interested in is that bottom leading order calculation, and we can plot. Let's at least have a look at this basic observation that one expects it to kind of follow how many types of quark you can produce. One expects R to follow that, and so here is plotted precisely R against some real data on the right hand side, and on the left hand side I've essentially plotted in Mathematica that's very, very basic formula I've just shown, which is just a constant until you can produce the next type of quark, and then it raises and so on. That's what you've got there, the thresholds for the different quark types. So let's look at that in a little bit more detail. So first of all, in the top, this is the lower energy region. So I said the root S here is on the y-axis, maybe that's been cut off, but and what you can see is this. Well, first of all, it's not straight lines because we've got all sorts of complicated resonances going on in there. But nonetheless, the basic level of normalization is actually set by what we expect within QCD. So if one just has up, down, and strained, you've got 4/9 plus 1/9 plus 1/9, which is 2/3, times the NC factor gives you a 2, which is basically what you see. That's that green line. And it basically agrees with observation. Of course, if you really want to get these things, you need to understand how these things are binding and forming resonances and all of that. But the basic normalization is there. It's 2, it's not 10, it's not 1. If NC was something different, it would be something different. So it's really telling you that QCD is along the right lines, if you like. If you add a charm quark in, you add the 4/9 there in that right-hand formula. And so you go up to, we've got 4 plus 5 plus 1. 5 plus 1 is 6 plus 10. 4 is 10 rather. So you've got 10 over 9. And so it's going to be a little bit larger than 3. So that's the green dashed line on the bottom. That's the naive leading order thing. The red is the higher order calculation. We'll come back to that in a bit. But again, the basic point is that the normalization sort of follows what you expect. And one can do it again for the bottom. And it's a rather similar picture. It kind of jumps up a little bit again. It genuinely, you do see that in the data. Okay, so a nice sort of idea that even this very naive picture here, the data sort of bears it out to some extent. Okay. Okay, let's go back to kind of some calculation. So the first thing I want to talk about a little bit, so I'll go to a new slide, is the Z resonance and the impact that has. So less of a QCD thing here, but it's certainly very relevant. So now, if we have root S is of order the Z mass, then 2 diagrams become relevant. So we've got this. Oops. So V plus E minus, that can be a photon then. There's the Q bar again. And just the same initial and final state now, but let me draw it as a kind of slightly different wiggle. And that is now the Z in the initial state, in the intermediate state. And we recall our Feynman rules. That if we associate a mu and a nu there, and we call that momentum P, then we've got a minus, or just forget about minus signs, just a G mu nu over P squared there. And our Feynman rules there will be G mu nu minus P mu over mz squared. Just again, P squared minus mz squared. And the first thing to say is that there gives 0, certainly if we're ignoring the quark and electron masses in the calculation. So, so to try that as an exercise, just use the Dirac equation for those fermions, and you'll soon find that's the case. So actually it's just a G mu nu. But what's more relevant for us is that what we actually want to be in here is, because what if we imagine that we're on the Z peak, P squared is equal to M squared, that thing seems to blow up. Now we know that's not the case, that really this thing has a finite Breit-Wigner width. So let me put that in there as I've done. So the Z is unstable and it will decay. With width gamma of Z. The other thing I should say is I'm going to make these blackboards available on the website. So, it's of course a bit more difficult when I've just got one slide at a time rather than a full blackboard for you to potentially get every bit if you're writing it at the same time. So if you miss something, you can refer. You'll be able to refer in real time to the kind of the notes, the blackboards. Having said that, my handwriting is not always perfect. So and also for this point of understanding things, it makes sense to write your own notes and follow what I'm saying, so that the next day, if you look back at the blackboards, you may not be clear what a one word or another word means potentially, and of course having your own handwritten notes in that respect as well will help. Okay, anyway. Yeah, the Z is unstable, it will decay, it has a width, gamma Z, we know this, right? Certainly something you'll be familiar with. And, in the narrow width approximation, this is just a sort of standard Breit-Wigner. Resonance. And in addition, let me just comment, but I won't go into the details because there's a problem on this. There's a more complex structure due to our VA coupling of the Z. So more complex with respect to in comparison to the photon case. So now we've got this thing here, the fermion and the Z, call that a mu, then that's going to go like this, VF gamma mu. So that's photon-like, just a gamma mu, but one also has the axial bit. So that's certainly more complicated, and there's an explicit problem about that. So I won't say any more. But again, perhaps let me just dip out of that and show you a slide on it, perhaps just to make the points that we have. I've just put in on the left-hand side, literally that expression I showed you before with the width as measured, squared it up, you get a nice resonance like that. And then on the right-hand side, you've got the data. Sure enough, well, the form of it, it's a resonance, but also the width of it sit nicely on the prediction. And then the overall normalization before the width, before the peak rather, is set by that R expectation as I discussed before. Okay. Okay, well, I've said, yes, it's a Bright-Wigner and fine, we're sort of familiar with that, but, just because you're used to something doesn't mean you necessarily understand it. And it's actually a rather subtle thing. Why is that there, right? Why is that there when I first wrote down the Feynman rule, and certainly what you learned in the standard model, course, there was that bit I put in red was not there. The propagator as derived from the Lagrangian just had that form 1 over p squared minus mz squared. So why have we just put this thing in by hand? Where does it come from actually in the context of our fundamental theory? So the width, the gamma that appears, in our Z propagator is precisely the usual Z to ... decay width. Okay. In other words, you do it in a different color. Gamma Z is proportional to some integral over some phase space. M of Z goes to X all squared, where that's, X is equal to E plus, E minus, neutrino, antineutrino, anything that can be produced kinematically, given that we have the invariant mass of the Z being what it is. So what's the connection here? Well, on the one hand, we've got something here, which I've written down, which is sort of an on-shell Z decaying to all of these particles, really genuinely decaying to them, and however many particles it's got will tell you about its lifetime and so on. However many particles it can decay to, rather. And on the other hand, I've put something in the propagator, in an internal propagator, and said that, that then dictates the actual width of the resonance. So what is the connection here? Why has it appeared at all? And the fact is, this is actually due to a rather subtle feature of quantum field theory, QFT. So what's the basic point? The basic point is this. This thing here, this Feynman diagram I've written there, this is not just given, or this process, let's say, is not just given by the above leading order diagram. Okay. So QFT tells us to consider higher orders, and in particular in this context, loop contributions as well. Loops as well. So let me draw that schematically, not schematically, but let me draw that as some examples. So yes, that's the leading order result as we just wrote it, but beyond that, one needs to include things like this and even things beyond that. So let's consider the impact on this. So let's consider, e.g., a scalar propagator. So just draw it as a line. And this is the Feynman rule. With that thing there, is the bare mass, the squared bare mass. So M0 is our bare mass, the parameter that sits in the Lagrangians. You saw a little bit of that in the context then of renormalization. But now let's go to next to leading order. Yes, so this is, sorry, the momentum P is, as usual, what's going through the propagator. So next to leading order, let me draw that again. One could have something like this. Okay, so that's just a loop. And what you're going to get there is, whereas bearing in mind above we've got 1 over p squared minus m naught squared from one of the propagators, like that one, we're going to define that to be this. Okay, in other words, this bit here, I'm just going to call some sigma of p. So one would calculate it in general. It would have some complicated structure. You need to do a loop, an integral over the loop momentum and so on. But we're not bothered about that here. Just, you know, one can define it to be that. So this thing here really tells you about, you know, the loop, contribution from the loop. Then we write put it as a blob, and next to leading order. So the next to leading order contribution to this propagator one could write as a series. Okay, one's calculated that one, but one could also straightforwardly, once we've done one calculation of the sigma, one could straightforwardly iterate and get 2 of the loops like this, and so on and so forth. So let me do one more. So, and so on. And let me write out what that is. So that's 1 over p squared minus m naught squared into 1. So that's just a leading order. Then we've got 1 over p squared minus m naught squared times sigma. That's what I've defined it to be there. So let's write that. And then you're going to find that you've got 2 of them there. Okay, 1, 2, 1, 2, and the usual 1 over p squared minus m naught squared again on the outside. So one simply squares it up, and that's it. One can go to further higher orders, but it would just be plus the same thing cubed, plus, 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 and that's it. So you'd have that that contribution calculated. Well, what is this? This thing here is a geometric series. So, you know, look it up on Wikipedia and you'll see that indeed can just be summed. You know, the sum of n equals 0 to infinity of this series, one can just write down, and this is the form it has. Okay. Which is equal to so a little bit involved, but when the dust settles, this is really what I want to get at, which is that the impact of loops in this case is to take us from our bare propagator, the thing we write down at leading order, to this. Okay. So in this case, we've got just a propagator, bare propagator, and in this case, we've included those loop diagrams as I've defined them. So I've skipped over some details of exactly what does and doesn't get included in there, so-called one particle irreducible contributions, but that's really not relevant here, but let me at least give a health warning about that. Okay, so the contribution of loops, missed the crucial bit, is to do that. And so we can sort of see where we're getting at here, because you go back to the original expression as it was there, and one could see that one has something on the bottom of the denominator which is proportional to the width, which wasn't there apparently in the leading order Feynman rules, but we apparently need to include. And now I've just told you that if one includes higher order loop contributions, one also gets a similar sort of thing on the bottom. And indeed, that's no coincidence. So perhaps that's got something to do with the width, and indeed it does. So this thing here, remember, is just an amplitude. So it's complex valued. And let's compare again versus what we want in the end. I've just written it as a general case. I'm not called it MZ, I've just called it M, it's the mass of the particle. Write that out again, it's a little bit messy. Okay. Yeah, so we're not talking about renormalization at all, but just to recall from your lectures before, you know, this is now the renormalized, i.e. the physical measured mass. So what we also have, and that's what is relevant to us, is the fact that, and so therefore, yeah, so making the association, sorry, before I go on, is that the real part of this thing, matching left to right, plus m naught squared should equal m squared. But it can have an imaginary part, it's a complex valued thing, and therefore, what is what we want. Okay, and if that is what we have, then this matches what I showed before, what I wanted, yeah, what I wrote down before in terms of the actual width. And indeed, you know, that is what we have. So now we recall our unitarity relation, which you saw, I believe, very briefly, but if not, please ask about it. We can talk about it in QED, QCD lectures. AKA, it's also called the optical theorem. It doesn't matter really what it's called, but just if you ever see that name, that's what you know what it is. So I won't go through all of the details here, but you know, let's start from a sort of general expression for a scattering amplitude. A. So just written in sort of quantum mechanics notation, if you like. And let me draw a picture for that. So we're going from some state n to some state m. Very schematic. So that's n. That's n. Then and that's our amplitude. Then we want the probability is the amplitude squared up. So let me write that first of all. It's the probability of going from n to m. But now let's sum over all of the possible states m. And what do we know about that? Well, it has to equal 1. So if you scatter n states, they've got to end up somewhere. Something's got to happen. So probability has got to sum up to 1. So, you know, maybe they won't scatter at all, and therefore, you know, the end state would also be included in that sum, or maybe they'll scatter to something else. When you sum over all possibilities, it needs to give you 1. And that seems like a rather trivial statement, but actually, you know, requiring that gives you a very strong consistency requirement. So i.e., let me write that down, probability that n ends up in some state, squeezing that in a bit there, equals 1. So here I am going to skip the details, but with a little work, it doesn't add too much to the discussion to do it, because really I've given you everything you need more or less to do it. This is equivalent to what? Let me write it down. Twice the imaginary part of the n to n amplitude should equal the sum over all possible particles that can be produced, integrated over their phase space. Let me write that again, sorry. like that. So let me draw that as a, let me draw that just to kind of perhaps give you a clearer idea of what's really meant there. Put a twiddle because of, you know, not really interested in the fact that it's an integral over the phase space and so on. The point is that on the left-hand side, we've got the amplitude, scattering amplitude for n to go to n. And on the right, and the imaginary part of that is related on the right-hand side for the cross-section or the decay width for n to go to anything that it's allowed to go for. And this is precisely what we want, okay? We precisely have, for us, this gives twice the imaginary part of our sigma. Remember, that's what I introduced here. That's precisely defined as that. You know, to v can exactly, you know, what's there. It's just n goes to n, so z goes to z, the z propagator. It's proportional to, so we don't care too much about the constants of proportionality here because we're not doing a full calculation. Z goes to x. And what is that? That's the decay width of the z. Okay. Sorry, let me stick with that. And this is equal to, when the dust settles, well, let me write it like this. That's obviously the decay width of the z. And if you do the full calculation, you end up with a z there, but an m there. But really the key element is the fact that we've got this proportionality. And, you know, this makes sense, you know, e.g., this even just makes sense from a kind of Feynman diagram point of view that, you know, why should these things be related? Well, you know, what kind of thing could impact on the Z propagator? Well, it could be a virtual loop of neutrinos, for example. And what kind of thing could impact on the Z decay width? Well, the Z could decay to neutrinos. So one has clearly at the Feynman diagram level, these things entering on the left and right hand side, and therefore it's in a sense not completely surprising that there is really formally this relationship between the two. So what are the implications for Pheno here? Actually, let me put it here. Well, by measuring the width, really measuring the actual physical width of the Breit-Wigner as it decays to leptons, for example, as it does at LEP. You're sensitive, as it did at LEP, to couplings of Z to all states it can decay to. So it's really one example of many of this idea. There's a rather deep relationship between things that can happen in loops and the actual particles that there are out there in the real world. And, you know, a lot of LHC physics is about precisely doing precision tests of things and trying to be sensitive to these sort of loop corrections to tell you about the standard model or what may be beyond it. And this is a very clear example of that. One has this actually rather deep relationship between the left and the right hand side, as I've written it up the top, and one can really measure these things. So let me show that. Get back to my slides. Yeah. So what we've got here is precisely the well, actually it's the Z width to hadrons as measured at LEP, so E plus E minus collider. And just by measuring the width of that thing, one can determine how many flavors of neutrinos there are. So of course, we're not measuring the neutrinos, we're not even measuring Z goes to invisible energy or anything. We're definitely not measuring directly that channel, but just by measuring the width of this peak, one can see that if you know, 2 neutrinos would push you above the line, 4 neutrinos would push you below, and one therefore has very clear evidence that actually there are 3 flavors of neutrino just from measuring that. You know, maybe another example actually, which I showed here, is that over the general point, which is that within the Higgs as well, if one imagines in a BSM scenario here that the Higgs mass can vary, for example, that actually the width itself, again, if you measure its width directly, depends on what it can decay to. And the actual standard model Higgs has got a rather narrow width because it can only decay to BB bar kinematically. But if you increase that width, so suddenly the decays to W pairs are allowed, you can see it increases very suddenly. That's precisely because of that. Okay, so let me go on a little bit. So I'll set the scene in the last 5 minutes or so, and then in the next lecture we'll go into a few more details. So we're sticking with E plus E minus to hadrons, but we're now going to forget about the Z for now, but we're going to talk about something else, which is so-called radiative. Let me write that again. Oh, no, that's okay. Radiative corrections. So we're going to stick to photon exchange. Oops, for simplicity. And we're going to think about, first of all, real corrections to this diagram. So let me draw the leading order again, like so. Okay, you know, I'd be a little bit lax and not always draw the fermion arrows, but they're always implied. And this is always E plus E minus goes to QQ bar. But we do that explicitly there. And, you know, as I say, it might be a bit lax in other cases. So NLO, real corrections. There are two possibilities. So NLO and QCD. So we're just talking about gluons being emitted from the actual quarks. And that. Okay. And yeah, so next time, we're going to calculate the impact of these.